Hi, today we're going to learn about types of immunoassays and the design of these assays so that as you're going forward looking at this type of analysis in the literature or in your coursework, you're able to recognize the different formats and categorize it. So the goal of an immunoassay is to detect an analyte without relying on any kind of enzymatic or other activity. This is really important when you have analytes that operate primarily in vivo by binding, and therefore they don't have an activity where they would cleave a substrate, for example. Okay, so we're just going to do it based on binding, no relying on the intrinsic activity of the analyte itself. Okay, and so the way that we do this overall is we're going to rely on being able to detect whether the analyte has bound to a reagent that can specifically bind it. Let's see, so we're going to detect the presence of analytes that have bound to another reagent, often an antibody. So for the sake of brevity, I'll just put antibodies here, but it's not always antibodies. Sometimes it's things such as DNA or RNA aptamers or other molecules that are designed to bind specific targets, okay? So detecting the presence of an analyte that bound to an antibody, okay? As you might imagine, a simple binding event does not itself create a signal that we can detect, and so we have to design in detection strategies here. And there's a variety of ways to do that we're going to go over in this and in subsequent videos. But before we get to that, I'm going to start with general formats of the assay. Okay, so let's talk about formats for the assay. All right, and so the first way that you can categorize immunoassays is based on whether your analyte or your antibody is in excess. All right, so first we have what's called non-competitive format. And then, of course, the opposite of that is competitive format. In the non-competitive format, the antibodies are in excess. And what that means is that you have plenty of spaces for the analyte to bind. And so we would say that the analyte is limiting. We could draw that, for example, if we have a surface like this, and we have antibodies on the surface, and we have plenty of them, and then we have analyte being added to it that can bind. And so there's always enough sites on the antibodies for analyte to bind. In contrast, in a competitive assay, it's the opposite situation. So the antibodies are limiting, and the analyte is in excess. All right, and so this requires a different type of design. Here again, if we had our antibodies on the plate, maybe we've made it so that there's hardly any of them, and then we coat, or rather, maybe we have the same number of antibodies, but we add a whole lot more analyte, more than could ever all be bound on the binding sites. And then we have to be able to distinguish whether the analyte that we have added is bound. And so often this requires a special type of assay setup where some of these are labeled, for example, with a fluorophore or some other detectable reporter. I'm going to go into a lot more detail on the competitive assay in a subsequent video, so don't worry too much about it for now. I refer you to that video if you want to hear more about how those assays are designed. But what I want you to take away right now is that we have these two assay formats that differ in terms of which reagent is in excess and which one is limiting. And either way, though, we can detect the analyte. Okay, all right, it turns out that there's also a second way to categorize immunoassays aside from which one is limiting. And so this is an orthogonal breakdown to the first breakdown that we just went over. And it's about whether or not the reagents are immobilized. So here we have two formats again. We have heterogeneous immunoassays, and we have homogeneous. In a heterogeneous immunoassay, we call it that because it's essentially phase separated, meaning that there is usually a solid phase. Some of the reagents are immobilized onto some kind of surface. Usually it's something like a plastic plate or a bead of some kind, either plastic or glass. Often it's that the antibodies are immobilized onto, again, some kind of bead or onto a plate. But sometimes the analyte can be immobilized too. Okay, the point is that there's a solid phase, and this allows washing, meaning we can wash off unbound reagents. Okay. In contrast, in the homogeneous immunoassay, it's all in one phase, usually in the fluid phase. Okay, and so what that means is we can't wash, and in fact, we don't want to if we've chosen this. And so just everything is in solution, okay? So whereas in the heterogeneous case, our antibodies were affixed and we could just add analyte and then wash off unbound stuff. Here we have antibodies in solution with the analyte. Okay. All right, again, there's going to be a separate video about homogeneous immunoassays and the way that we would use those and what types of detection methods are appropriate. So I refer you to that video if you're interested in those. For today, to learn about immunoassays in general, we're going to focus on heterogeneous non-competitive immunoassays. All right, so focusing on homogeneous and non-competitive assays, I'm going to start by sharing a classic example, which is called an ELISA. And so if you've done any reading at all about immunoassays for bioanalytes, you've probably run into this. And so what we're going to do is think about kind of how are these typically set up, and then I'm going to tell you what the various options are. All right, so the common setup is that we have a surface of some kind. This could be a plate made out of plastic or metal or glass. So usually some kind of plate. It's most often like a polystyrene plastic plate, like a 96 well plate or something like that. Or it could be beads, such as nanoparticles or magnetic beads, something like that, that you could easily pull out of solution, for example. But it could also be the surface of an electrode or some other type of probe that you could insert into a solution. So there's all kinds of options here. Onto that surface, it's very common to adsorb a reagent next. And so we're going to start with learning about if you adsorb antibodies. Okay, and so here we would call the first antibody that is adsorbed the capture antibody. I'm going to abbreviate it AB. And then you can add your solution that has analyte in it. Let's say it looks like this. So we bound the analyte to this antibody. Okay, so here's our analyte. Actually, I should say that before you add the analyte, after you've coated with capture, so you coat with the capture antibody, then you do something called blocking, which you do second. So I'll put it here, blocking. And so what this is usually some kind of protein mixture, such as bovine serum albumin, or some people will use dried milk because it's filled with albumin as well. People use all kinds of things. Some people will use serum, but BSA or milk are the most common. And the purpose here is to obstruct anything else from binding the empty spots on the plate, right? So that unfortunately the antibodies can't take up all the space. And so we want to fill in the rest with some kind of protein that will block the surface so that no analyte binds to those spots, right? All right, so we've added our capture antibody, our blocking reagent, and our analyte. And then we ask, hey, how can we tell that the analyte bound the surface? So far, we cannot. And so in the classic ELISA format, we add another reagent called a detection antibody. This is an antibody that is also specific for the antigen, but it needs to bind in a different binding site than the capture antibody did. And then we need some kind of detection modality, and there's a lot of options here. A very common modality would be that we would have this detection antibody linked to an enzyme, and then we can add a substrate for that enzyme as a final step, and the enzyme will cleave it or otherwise make it have a signal, and then we have a product that we can detect, okay? And that's what we detect. Okay, so we have this, you can see very many steps, right? We have the capture antibody, we have the blocking, then the analyte, then the detection antibody, and then either in the same step or in a different step an enzyme, and then the substrate. And so there's at least 5 or 6 steps here. You can imagine how it might be easy for there to be errors if it's being done by hand. But this is the overall setup of a classic ELISA system. The ELISA stands for enzyme-linked immunosorbent assay. Okay, so the E is for enzyme. All right. It turns out there are other detection methods, such as using fluorescence, that we won't go into today. All right. All right. So this is the classic step, but the classic setup. All right. But the issue is that there are actually multiple ways that one could choose to set up an immunoassay. And I want you to know the options because you're going to be choosing those as you design your own assays. And also you may be needing to recognize those in the literature. Okay. So let's look at the variations. Okay, so one variation is to have direct versus indirect capture. And what I mean by that is that if you have indirect capture, it's what I just drew, where you coat with your antibody, and then you use that to immobilize your antigen. Okay, so that's indirect. Direct is where you just directly coat the antigen on the plate. Okay. And so the difference here is that if you might think about when might you use one or the other, the direct capture is simpler because there's fewer steps, fewer reagents, therefore it's lower cost. You don't need this extra antibody, right? But by using the indirect capture, it's actually a lot more selective. And so what we can do here is use a complex sample such as serum, for example, or saliva, and you'll only attach, in the end, attach to the plate your antigen of interest via the antibody, whereas if you put serum over the direct plastic plate, everything in the serum would absorb, okay? And so we get this much more selective binding with the indirect capture. Okay. Similarly, there's also direct versus indirect detection. And so what that means is that regardless of how you chose to anchor the analyte to the plate, let's say that we chose the indirect way in both cases. So maybe I have my antibody on the plate and I've done my blocking, and then I come in and I add my reagent or my solution that has my analyte in it, and it binds, and I wash off everything. Okay, but now I have to choose how I'm going to detect. So in direct detection, we have our detection antibody, and it might be directly labeled, like I said before, say with an enzyme or a fluorophore or whatever it is. Okay, so this is the simplest. Again, the other option is that you come in with an unlabeled detection antibody, and then you bring in yet another antibody that binds to it, and then that secondary antibody has the label. Okay, so we call this here, this one is called a secondary antibody. All right, you might ask yourself, why would you ever bother having yet another antibody there? And you might imagine it's because it gives you a couple benefits. One is that it allows you a little bit more modularity of design. What I mean by that is that here, your detection antibody doesn't need to be labeled. It can just be, say, analyte and without any extra label. And then you can come in with an antibody that's specific to this anti-analyte. And so we don't need to have as many conjugated detection antibodies here. For example, it's very common to use an anti-isotype antibody for the secondary, meaning it's going to be anti-goat IgG, for example. And then here we would use a detection antibody of a particular isotype. Okay. So that's how we usually set those up. In contrast, in the direct detection, you have to go and label every single detection antibody that you're going to use for any analyte. And so you can imagine that can become a little bit costly or awkward. In addition, you also get some amplification from the secondary, from the indirect detection. And that's because although I've drawn it with just one detection antibody binding, because these are often binding the FC region, usually multiple of them can bind at a time. And so you get some amplification here. You can imagine that can increase the sensitivity of your assay, meaning it gives you a lower limit of detection. Okay, all right. So far we've talked about that we have direct or indirect capture, and we have direct or indirect detection. When you have the combination, like I drew up here, of an indirect capture with using a detection antibody, whether it is direct or indirectly detected, this combination is called a sandwich setup. And we call it a sandwich because we have sandwiched the analyte in between the capture and detection antibody. And so you'll often see that term. And that requires that the two antibodies bind to different epitopes. In particular, not just that they're different epitopes, but that they actually bind to non-overlapping epitopes, okay? So that's what a sandwich immunoassay is. All right, let's step back and review what we've learned. We learned about direct and indirect capture, direct and indirect detection, and then also this terminology about sandwich immunoassays and how they can be built up if you use an enzymatic reporter to make an ELISA. So let's just very briefly go over one last type of variation, which is the choice of reporter. We've already talked about using enzymes. And so here we can say one is an enzymatic reporter versus what we might call a linear reporter. And what usually that means is something like a fluorophore, or perhaps a group that's electrically active, and then you're going to use it for amperometry. Okay, but let's just take fluorophores as the example. And so here, this would be if, say, we had an assay, it could be any type of capture. Let's just draw direct capture for simplicity. And then we have either type of detection, whether it's direct or indirect, but we'll make it direct for simplicity. And then now we have our label. So here we could have an enzyme, and now you have to add a substrate and you look at the product, okay? Or you could just have your enzyme directly labeled with something that will fluoresce, okay? All right, so let's ask ourselves what would be the relative advantages and disadvantages. You might imagine the linear one, again, is the simpler one in some ways because it has fewer steps. You don't have to add a substrate and you don't have to wait for a product to react. Okay, but on the other hand, the enzymatic reporter gives you amplification. So just like before, we got amplification from using our indirect detection. Now we also get amplification if we choose an enzymatic reporter. And so again, this will lower your limit of detection. All right. So we get much higher sensitivity with enzyme reporters, but fewer steps and fewer reagents with a fluorescent reporter. And sometimes fluorescent reporters can also be easier to multiplex if that's important to you, like if you need to measure multiple analytes at one time. Okay. All right. So I'm going to stop here. Okay, let's just look at what we learned. We learned that these different ways of designing an immunoassay in terms of different capture modalities, different detection setups, and also different choice of reporters. We learned about the most common setup, which is an ELISA, which uses indirect capture, indirect or direct detection, and then usually an enzymatic reporter. And then we also, going back to the beginning, we learned about these different formats for assays. And so if you're interested in learning more about immunoassays, I refer you to the videos on competitive immunoassays and homogeneous immunoassays in order to learn more about those. Thank you.